have almost half of the class in the session already. So we should start our class now. All right. So for today, we are going to continue with the topic advanced convective heat transfer. Okay, so last week you all learned how to formulate the temperature profile, right? So that is your learning outcome number 3. All right. So week 4 and week 5, you all learned about the conduction, convection, and radiation. Then last week we talked about the temperature profile. So okay, uh, this is okay. Yeah, this is for today. So now, for today, the first part you'll be introduced to a few dimensionless number, like the Reynolds number, okay, and the Nusselt number, and also the Prandtl number. Okay, so then our topic today here, it will focus on the different correlation that we are using it to find the H value. Because for so far, whenever you calculate the rate of heat transfer, right? So it's where you just apply the equation, the Newton law of cooling, where you have the convective heat transfer coefficient multiplied to the area, then multiplied to the temperature difference, right? But how do we, okay, so, but how do we actually obtain the H value? So for the past, most of the time, the H value is provided to you, right? So our topic today will focus on how are we going to calculate this H value, okay? And then after finding it, then we'll apply it to calculate what is the rate of heat transfer. So for this H value here, it depends on a few things, right? So one of it is whether the flow, right? Because when we talk about convective heat transfer, is about the heat transfer between a moving fluid, right? So you have a moving fluid. It could be gas or it could be liquid, all right? And a surface or solid surface. Okay, and when there's a temperature difference, so let's say this is T1 and then your environment is at temperature TA, okay, and T1 is greater than TA, then heat will transfer by convective, right, convection. Okay, so then, but okay, the H value here, it also depends on whether the heat transfer is occur inside or outside a geometry, right? It depends whether it's inside or outside the geometry, right? And it also affected by various geometry, right? One thing is the location, all right? Second thing is the geometry. And then the third thing, it will also be affected by the flow behavior. And the fourth thing is it will be affected by the fluid properties. So these few factors will affect the H value. Okay, so the second part, right? So we are going to look at correlation for calculating the H value for flow, for convection, all right, in pipes, all right. So whether it's in laminar, turbulent, or transition region. Okay, then after that, we are going to look at heat transfer outside various geometry, which cover plate, all right, and then sphere and cylinder, flow past outside a cylinder, or banks of tube. We are going to look at the case of banks of tubes as well. All right. And then the last part would be the correlation for calculating the H value for natural convection. Okay, so these are the 4 parts that we are going to discuss today. And then, so it will be aligned to your second learning outcome, which will focus on analyze the thermal behavior of engineering system using the laws of conservation. All right, so these will only appear in your final exam. If you recall back the module information, all right, so your test on week, I think it's week 12, right? It focus only on your learning outcome number 3, right? Week 12 test, okay? So, but you still need to focus, yeah, okay? Prepare well for this. I think because this, I think it's around question 3 or question 4. It's a 25-mark question, okay? So now let's look at the first part here. So why is it important? Why is it convective heat transfer important? Because if you recall, right, so for an industrial process, usually we will need to meet certain productivity or production capacity to deliver to the client, right? So which means, of course, then it will be good if the rate of the process could be increase, then it will be, we can complete it faster, right? So same goes to heat transfer. So we know that heat transfer by conduction, it will occurs at a very slow rate, all right? So if we could speed up, all right, speed up the speed or the rate of the flow of the fluid, then it will also contribute to convection, right? Then it could be, we could also speed up the rate of heat transfer. So a few examples where you may encounter convective heat transfer. So these are some common examples. It could be in shell and tube heat exchanger, right? So let's say in the utility section, right, where you need to supply hot water or or the cold water, right, processed water for certain process, right, or the simple double pipe heat exchanger that you all have learned last time during thermal and heat transfer, right? So, and then the plate heat exchanger, where usually it comes in several plates, and then you have different fluid flowing in different sides of it, okay? And plate fit fin exchanger, the spiral heat exchanger, the A-cool, or the cooling and the condenser, and then agitated vessel, for example, the CSTR, right, and the fired heater, right? So these are some example of the application of convective heat transfer, right? So and with this, you can notice that each of this equipment here, it involves different geometry. Like the shell and tube heat exchanger, you have a lot of tubes, right? A lot of tubes for heat transfer between two different fluid without mixing, right? Well, plate heat exchanger, then it comes in a plate form. Okay, so now let's look at this. So for the past few weeks, right, so we have discussed about also the convective heat transfer. So this is the equation that I mentioned just now. The rate of heat transfer equals to the convective heat transfer coefficient multiplied to the cross-sectional area that perpendicular to the direction of the flow, right? But if it's convective heat transfer, then it depends, all right? It's not really perpendicular then, right? Okay, it depends on the fluid that flow past it. Then the temperature, all right, of at the surface perhaps, all right, then minus the temperature of the surrounding, or it could be the other way around if the wall temperature is higher compared to some other temperature. Okay, so convective heat transfer coefficient, it has the unit of watt per meter square Kelvin. All right. So when we talk about convective heat transfer coefficient, so if you recall back, right, so this is how its temperature profile looks like, right? It will be a curve, right? As compared to the conduction, it's a linear curve, right? So now why do we have a temperature drop at this section here? So you can see that there's this one here, right? There's a flame that is being indicated here. That's where if you compare to the velocity profile, right? So if you compare to the velocity profile, right? So usually there would be friction to fluid flow, right? So at a region which is very close to the surface is where most of the heat will then be will be transferred by actually conduction, right? Because the fluid flow at a very slow rate. So same goes to here, right? So that's why actually when we talk about convective heat transfer, right? Convective heat transfer is actually a combination of conduction and convection, right? So where this section here, this two section here, because of the very slow or the low velocity or the fluid flow at a very slow rate, so most of the heat transfer is by conduction, and therefore it experiences the most temperature drop, right? So you have a very high temperature gradient at this section here. Or you can also say the resistance, right? Major resistance to heat transfer actually happens at this flame here. Well, when it's further away from the surface, because there's a lot of eddies, right, that helps with the mixing, right? So that's why you can see that the temperature almost level off. Okay, so this is how you can plot or sketch the temperature profile. All right, so for combined convection and conduction. Now, so what are the three-dimensional number which are very important when we want to correlate the H value with some of the fluid properties, all right, or all the what should I say, parameters that I mentioned just now that may affect the H, right? Whether it's fluid properties, whether it's geometry, or whether it's the flow behavior. So this dimensional number, right, then it helps us to relate all these factors here with the H value. So for example, the Reynolds number, then it tells us about the flow behavior, right? Which is rho Vd per mu. So this is the velocity. Okay, and then this one, the D, it depends whether you're dealing with a sphere or is it a cylinder. All right, then we will be using diameter. Whereas if you are dealing with plate, all right, if it's a plate, then we should use the length of the plate. All right, and then most of the time, the density and the viscosity, we will take it as the density and viscosity of the bulk fluid, right? The bulk fluid. Okay, and later you need to take note, right? So when we are going to find all these properties here, it depends on whether the flow is inside or outside the pipe. So we will need to determine what is the temperature that we should refer when we are going to find out what is the density and viscosity value. And same goes to, you can see here, the thermal conductivity, the specific capacity, right? So all this, it depends on the temperature, which temperature should be referred. So I will highlight it later, all right? So then another one, the Prandtl number. Prandtl number is, so it's related also to the flow behavior as well, and some of the fluid properties, which you can see here, the thermal conductivity. So this section here, right, the mu divided, this one multiplied to specific heat. So this is the specific heat capacity. Okay, you take note, this is specific heat capacity. K is the thermal conductivity. Right, specific capacity multiplied to the viscosity of fluid divided by the thermal conductivity, it gives us the Prandtl number. So actually later when you refer to the tables, right, those tables, they may have given provided you the Prandtl number directly. So it's okay that you use them directly, right, instead of calculating it from scratch. All right, it will be accepted during your final exam. All right, so what is Prandtl number? Prandtl number is actually the ratio of momentum diffusivity, right? So you can see you have a viscosity term here. It's a ratio of moment, if you look at it, momentum diffusivity to the thermal diffusivity, right? Thermal diffusivity. So we mentioned thermal diffusivity because here the heat transfer, right, is by conduction, right? When we have the thermal conductivity term. Okay, so we will also talk about it in a later chapter. It also related to the velocity profile and the thermal boundary layer, right? The velocity boundary layer and the thermal boundary layer. But I'll stop here, just here, all right, the general introduction for today. All right, so then as for Nusselt number, all right, so Nusselt number is the convective heat transfer coefficient multiplied to the diameter. So again, it could be diameter or the length, right? Dependent, you are dealing with, let's say the sphere and the cylinder, then we'll be using diameter. L is for plate. All right, so Nusselt number is equals to the convective heat transfer coefficient multiplied to the diameter divided by the thermal conductivity. So it's as if this is a ratio of convective transfer to thermal diffusivity, right? Okay, so now how do we relate all this together? So you can see now, right, this is the H value. So now in general, so how you convective heat transfer coefficient is related to all other this geometry, the fluid properties, the flow behavior. So the geometry here, then it refers to whether this one, the D and the L that we are using. So right, so now the correlation, it actually takes this form here, where your Nusselt number is equal to some coefficient multiplied to the Reynolds number to some power of m, and then multiplied to the Prandtl number to some power of n. So in general, later you see most of your correlation, it takes this general form here. All right, so which here you can see your Nusselt number is hd over k, for example, right? Your Reynolds number is rho v d per mu, all right, the mu to the power of m multiplied to Prandtl number Cp mu over k. Now, this is how the convective heat transfer coefficient, right, the H value is being related to the geometry, to the fluid properties and the flow behavior. All right, so which is what I mentioned just now, right? So is there any correlation between these three-dimensional numbers? So yes, right? So but there are correlations. So this is only the general equation, right? The one that I highlighted in yellow is a general equation. So all your C value, the N value, and the N value, it will be different, right? Depending on the type of flow. All right, so you'll notice that some correlation, it can only be applied for certain range of Reynolds number or Prandtl number, right? And then for different types of geometry, we will have different correlation as well. And then also whether the fluid is flowing inside or outside the geometry. right? So, okay, that's the general introduction about the dimensionless number. So now the second part, we are going to look at the correlation that we are going to use to find the H value for forced convective heat transfer inside the pipe. So there will be three different correlation, right? For whether it's laminar, it's turbulent, or the transition flow. Okay. So, okay, I'll need your help. If you notice your friend is joining the session now, please help to admit them into the session. Okay, thank you. All right, so now let's look at the first correlation. Now, let's say if we have a laminar flow in pipe. So, laminar flow, all right, is given by this Reynolds number that is smaller than 2100. All right, so then your Nusselt number, which is equals to, so because it's flow inside pipe, right, so which means it's something cylindrical shape. So that's why we are using the diameter, right? So the average convective heat transfer coefficient multiplied to the diameter divided by the thermal conductivity is equals to 1.86, then multiplied to the product of Reynolds number, Prandtl number, then diameter over length, right? Then to the power of 1/3, then you multiply it to the ratio of the, so this one we say that this is the viscosity of the bulk fluid, right? Bulk fluid. While this one is the viscosity at the wall temperature, right? At the wall temperature, right? So this ratio to a power of 0.14. Now, so this one, then I will not introduce further now on. So if let's say you see that it's Reynolds number, then which means it's rho d per mu. If it's Prandtl numbers, then it's the Cp mu over K, which this value here you can also get it directly from the table, right? If you don't want to calculate it. Now, so you have to take note when we are going to find the H, right, using the correlation for the case if we are dealing with forced convective, right? Let's say if it's forced convective heat transfer inside pipe, right? So write down this very important thing in your note, all right? So for all the properties, all right, so which mean properties like the density, the viscosity, specific capacity, or Prandtl number, the thermal conductivity, all the properties, it will be evaluated at the bulk fluid temperature. Okay, this is very important. You have to remember this. Only for any flow in pipes, all right, when we are going to use the correlation to find the H value, all the properties, right? So which here, density, the specific capacity, all right, all this sample example here, it should be evaluated at the bulk fluid temperature, right? Except for, right? So except for the viscosity at the wall temperature, except for this term only, right? Because in the next section, when we are going to look at correlation to solve the H value for flow outside those geometry, right? Those properties, it will be evaluated at other temperature. Okay, so take note of this one. Okay, so you may want to highlight this in your notes, right? So now, then if you want to apply this correlation here, take note, you have to make sure that this term here is being fulfilled. The Reynolds number is smaller than 2100, and also the product of the Reynolds number, Prandtl number, and the ratio of D to L, it should be greater than 100 as well. Okay, so for this correlation to be valid. All right, so then now, if you have found the H value, so in most of the time, right, we are calculating the rate of heat transfer by using the convective heat transfer coefficient multiplied to A, then multiplied to the temperature difference. Now, sometime, right, it might be what happens in the fluid flow in pipe, right? So let's say we know that the fluid actually enters the it enters at temperature TBI, all right, and then it leaves the pipe at temperature TBO, right, and then but the wall temperature here is held at TW. So which means, right, what happens here is your bulk fluid temperature, all right, it varies along the pipe. Instead of here, when most of the time when you do calculation, is for example, it could be the bulk fluid temperature minus the wall temperature, assuming that your bulk fluid temperature is constant throughout the pipe, right? So this is what happens most of the time when we do the calculation of rate of heat transfer. Now, if let's say if this kind of case occurs, right, where your bulk fluid temperature varies along the pipe, so this is how we will calculate the temperature difference, right? So you get the temperature difference at the inlet, right, between the wall and the bulk fluid, plus the temperature difference between the wall and the bulk fluid at the outlet. So this refers to outlet, right, and this refers to inlet. So you get the sum of both temperature difference at inlet and outlet, then you divide it by 2, right? So this is if there's variation in the bulk fluid temperature. Okay, so now sometimes, right, this HA value is like the thermal conductivity K, right? So theoretically, we know that the thermal conductivity, it will varies with the range of temperature that is being investigated. So most of the time when we do the calculation, we assume that the K value is constant. So here, the HA value, the average convective heat transfer, it will also be affected as well. It will vary as well if there's a very large temperature difference between the pipe wall and the bulk fluid. All right, because you can see, right, when we calculate this, all right, so we take into consideration as well for this one. So if the variation is very large, then this H value here, it will be affected, right? Same goes to the diameter, the pipe diameter as well. It will also affect the H value, where it could possibly increase the H value, right? If we have very large pipe diameter or very large temperature difference. Okay, now this is for laminar flow in pipe. All right, then the next one, this correlation here is we can apply it for turbulent flow in horizontal tubes, right? For Reynolds number that is greater than 6,000. Okay, so this part here is actually your Nusselt number. All right, so you can see, right, so it's equals to some correlation here, right? So a coefficient multiplied to a Reynolds number to power of n, and then your Prandtl number to some power of n, and they include also the viscosity here, the ratio of viscosity at bulk fluid temperature divided by the viscosity at the wall temperature. So you can notice also depending on the Reynolds number, all right? So this value here, the C value, the power m and n value, it then differs from the one in laminar flow. Okay, so take note here, besides you need to fulfill the condition that the Reynolds number is higher than 6,000, right? So for the condition to apply this equation, right, so we need to make sure also the Prandtl number is between 0.7 and 16,000, and then the L over D is higher than 60. Okay, so this is for turbulent flow, the correlation for turbulent flow. Okay, now same thing, right? So similar to laminar flow, right? The equation for calculating the rate of heat transfer, yes, is this one. But if let's say there's a temperature variation in the bulk fluid, right? So this part here for the temperature difference, then it can be calculated as the average of temperature difference at the inlet and the outlet, right? Between the bulk fluid and the wall. Okay, all right. So yeah, no worries. You are not expected to memorize this. All right, no need to memorize everything. All the correlation that you see today, or even all this condition here, you are not required to memorize it. All right, so you will be provided with the correlation and the condition, right, in the last page of your final exam, where you can choose, right, which one you should be using. And usually it will be focused on that particular type of geometry. You'll not be provided with all different types. All right, so no worries. Yeah, okay. So now let's try out this example here. All right, then perhaps you can understand better how we should apply the correlation. Okay, now let's look at this one. Let's say if we have heating of air in turbulent flow, right? So okay, now here we have air that is at 206.8 kilopascal pressure and an average temperature of 477.6 Kelvin is being heated as it flows through a tube. So the tube has a diameter, inside diameter of 25.4 mm. And then the air is flowing at a velocity of 7.62 meters per second when it's being heated. So the heating medium, all right, so heating medium is at 488.7 Kelvin steam condensing outside the tube. So since the heat transfer coefficient of the condensing steam is several thousands watt per meter square Kelvin, and the resistance of the metal wall is very small, so it will be assumed that the surface temperature of the metal wall in contact with the air is 488.7. All right, so here they ask you to assume that the T wall, right, the TW, the wall temperature is 488.7 Kelvin, right? So what happens is like this: you have air that is flowing, right? Air that is flowing through the pipes, all right? And then, okay, and then what happens is you have here outside, let's see, a steam that is condensing, right? Steam that is condensing, and they mentioned that the H value is very high, and same thing here, the resistance to heat transfer in the pipe wall is also negligible, right? So the H value is very high. So your temperature of the steam is almost equal to the TW, right? So which is 488.7, right? This is what they mean. Okay, so now you need to calculate the convective heat transfer coefficient, assuming that the L over D length divided by the diameter of pipe is greater than 60. Now, it's being mentioned here because if you recall back, right, so the data given in the question is only the diameter, 25.4, but they didn't mention what is the length, right? But we do not need to calculate it because besides finding the H, you only need to solve for the heat flux, right? So we do not actually need to know the area. Okay, now, so although it mentioned that it's heating of air in turbulent flow, now before we can proceed, right, we will then need to calculate what is the Reynolds number, right? So we need to calculate the Reynolds number. So we know that Reynolds number, okay, so it's given, okay, let me write it here. So for Reynolds number, so we know that it's rho VD per mil. All right, so velocity is given in the question, diameter is given, so we'll need to find out the density and the viscosity. Now, but then how do we solve it? Okay, so if you recall back, all right, so when we have flow in pipes, all the fluid properties must be evaluated at the bulk fluid temperature. So which means it will be this one, right? TB is equals to 206.8 kilopascal. Now, but there's an issue here. Oh, sorry, that's, oh my God. Temperature is this one, this one, okay? TB, bulk fluid temperature is 477.6 Kelvin. Now, but there's an issue here, which is this, the pressure. Because if you look at your table, right? So I've uploaded this table also right under week 6, right? You can download it. If you look at the table, right? So for physical properties of air, all this data here is actually compiled for when air is at 101.325 kilopascal. But now, if you look at the scenario, the air is flowing at 206.8 kilopascal. So which means we'll have to do something, right? Some conversion with the properties, right? So that we can obtain the properties of the air, which is at this particular pressure here. Now, so if theoretically, all right, only density, it will be affected by the pressure moves, while viscosity, there's negligible effect on it. So now, how do we solve for density then? Right, so the density is proportional to pressure, but it's inversely proportional to temperature. Right, so then we'll need to find out. Right, so let's consider standard this one when temperature is at 273. All right, and then pressure, which is at 101.325. We'll need to check what is the value of the density. All right, so if you check, okay, so table A33 at temperature 273.2, okay, I'll write here to Kelvin, right, at 101.325 kilopascal, right, the density is 1.293 kilogram per meter cube. Okay, so I'll note it here, 1.293 kilogram per meter cube. Okay, but then what would be the density when the pressure is at 206.8 kilopascal, and then when temperature is at 477.6 Kelvin, right? This 1.293 is for air at 101.32, let me see, 101.325 kilopascal, and temperature at 273.2 Kelvin, right? So, which means you need to do some calculation, right? Okay, so when I arrange it like this, then you can see the relationship really, how we should rearrange it to get the answer for the density, right? Density at 477.6 Kelvin and 206.8 kilopascal, right? So now if we calculate mathematically, right, so which means the density at a new temperature and pressure, it will be equals to, okay, let's rearrange it. So it will be equals to 1.293, right, kilogram per meter cube, okay, multiplied to, okay, let's see, let me rearrange it, multiplied to 206.8 divided by 101.325. So I'm not writing the unit because it will then be cancelled out. All right. Then next thing is multiplied to 273 Kelvin, right? 273 Kelvin divided by 477.6. Because if you look back at what I listed here, right, it's as if you are equating the ratio, right? It's as if you are equating the ratio. Then we just rearrange it. Okay. So if you calculate this, the answer for the density, let me check. Yeah, the answer for the density, it should be around 1.509. 1.509 kilogram per meter cube. Okay, is it okay so far for this density part here? Any questions so far on solving this density, which is at other temperature and pressure? No questions so far? Okay, all good. Yeah. So take note, especially I think your assignment, right? The assignment, your question 2 of your assignment is regarding this topic here, right? Where you are going to find out what is the correlation that you should be using, right, to solve for the H, then calculate the rate of heat transfer. So if the process is at certain other pressure, you have to take note of this part here where you need to do the conversion. Okay, so you may want to highlight this in your notes, right, to help you to remember this necessary step. Okay, if the process is not occurring at 101.325 kilopascal. Now, it's only density of air that will be affected by the pressure and the temperature most, while the viscosity to a very less extent. So then we can proceed to this calculation of Reynolds number. Okay, I'll do it quickly. So 1.509, right, kilogram per meter cube, then multiplied to the velocity. Okay, velocity is 7.62 meter per second. Right, diameter is 25.4, 10 to the power of negative 3 meter. Now that will need to divide by the viscosity. So viscosity of air at, so we need to evaluate at the bulk fluid temperature, right? So which means is this one here, 477.6. So let's check. So at temperature 477.6, the viscosity of air, so how you read it, you have to be careful, is 2.6, but don't forget this part here, right? You can see, right, it's 10 to the power of 5, right? What is reported here is your viscosity, then 10 to the power of 5. So when you write it here, it should be 2.5, then 2.6, right? Let me check. Yeah, 2.6, 10 to the power of negative 5 kilogram per meter second. Okay, so if you complete this calculation, the Reynolds number should be equals to 1.122, 10 to the power of 4, right? Which, if you recall back, right, so if we want to determine which correlation that we should be using to find out the H value, so you have two correlation, right? One is for laminar flow, this one here, right? But it only applies to Reynolds number less than 2100. So then we have another correlation, which is for the case where Reynolds number is greater than 6000. So that's why we should be applying this one. If the scenario didn't tell you that it's turbulent flow, right? So you have to check the Reynolds number, right? So we'll be using this one, right? So that's why you can see I copy out this correlation already, right? So this is greater than 6000. So we can conclude that yes, this is a turbulent flow. Okay, then you can substitute this value here into the correlation. All right, and then Prandtl number, let me see. Okay, let me see. So I'll write it out here also, 0.027. All right, the Reynolds number is 1.122 10 to the power of 4, power of 0.8. Now let's check the Prandtl number. So the Prandtl number at bulk fluid temperature is given here is 0.686. All right, so substitute 0.686, right, to the power of 1 over 3. Then we'll need to substitute the viscosity at the bulk fluid temperature and viscosity at the wall temperature. So at bulk fluid temperature, 477.6, okay, viscosity is 2.6 that we found just now. Okay, so 2.6, 10 to the power of, let me check. What's the, okay, -5, all right, then divided by the viscosity at the wall temperature, which is 488.7. Oh, so we can see we do not have data at 488.7, right? So which means you then need to do interpolation, right? So you have to do interpolation to find out what is the viscosity at wall temperature, which is at 488.7. So now let's say we have done the interpolation because of time limitation. Okay, I'll write down directly. Okay, so it's 2.64 10 to the power of -5. So it definitely will be a value that lies between these two values here. Okay, so then the next thing is, okay, we are finding our convective heat transfer coefficient. So we substitute diameter here, 25.4 10 to the power of -3 meter. Okay, divide by thermal conductivity at the bulk fluid temperature. So which is this value, 0.03894. All right, 0.03894 watt per meter Kelvin. Right, so now, that is actually not that difficult, right? So it's actually just finding your data at the bulk fluid temperature or the wall temperature, substitute it into the correlation, then you can calculate what is the H value. So if you solve this, the H value should be equal to 63.2 watt per meter square Kelvin. Okay, so now, but that's not the end of the question, right? So you are requested also to find the rate of heat transfer, the Q value. Okay, so and we know that the rate of heat transfer is equal to HA multiplied to the temperature difference, but we are solving for the flux, right? So which means it's H multiplied to temperature difference, or in this case here, it's actually it's the wall temperature that is higher, right? So TW minus the bulk fluid temperature of air. So which means it will be equals to 63.2 watt per meter square Kelvin, all right, multiplied to 488.7 minus 477.6 Kelvin. Okay, temperature difference in Kelvin. So if you solve this, the answer should be equal to 701.1 watt per meter square. Okay, all right. So, any questions so far, everyone? Is it okay? Is there any questions so far?
Dr. Shaw,
Mm-hmm.
I want to ask for the air at the wall condition, right? Is it still under the same pressure, or is it normal atmospheric pressure?
The air is flowing at this pressure. It's given in the question.
Understood.
Here, it's like you can imagine that there's a compressor that actually compress the air at this pressure to force it flow through the tube. Okay, all right. Any other question? As no, I'll continue a little bit further, right, to complete this part here on flow inside tube first, yeah, then we'll take a break. Now, there's one more part here. Okay, so the full solution is provided in your lecture notes, no worries. Okay, now, so we have covered the correlation for laminar region and also for the turbulent region, right? So how about the transition region, which is between 2,100 and 6,000? Now, so if it's in the transition flow region, right, then we cannot use the two correlation that you are being introduced just now. Instead, we will be using this plot here in figure 4.5 to this one here to find out what is the H value. Okay, so now you can see here, all right, so depending, because we don't have the correlation, because it depends also on your L over D, right? You can see for different ratio of L over D, all right, so this is the transition region. Let me highlight it to you, right? 2100 to 600, 6000, right? So you can see there are different curve in the transition region. So what we'll need to do is the same. You need to calculate it's actually a Reynolds number. On your x-axis here is actually the Reynolds number. If you recall back, it's rho v d per mu, right? So you have the viscosity, right, and the diameter. So this G here is actually, they call it as a ratio of the mass flow rate to the cross-sectional area. But it's also equivalent to density multiplied to the velocity, right? So you identify here what is the Reynolds number, then you need to calculate also what is the L over D ratio. So let's say if we have identified it somewhere here, and then you trace it to the left-hand side on a y-axis, what would be the intersection? So then you equate it to, so let's say 0.0032, right? So you equate it to this y parameter here, right? Substituting all the properties of the fluid, right? Evaluated at the bulk fluid temperature, except for this one, right? That you need to evaluate it at the wall temperature. Then we should be able to find what is the average convective heat transfer coefficient for flow in the transition region, right? So this is the only special part. All right. So I think should be fine, right? This is just introduction. Now, I think before we proceed to this next part, for today, I'll give you a very, very short break because we have a lot to cover. All right. So let's take a break for 3 minutes. 3 minutes. All right. Then you come back at 11. You come back at 10:52. Right. Just 3 minutes. Right. For you to settle down, relax a bit. So I hope you are back. All right. So let's continue with the third part of our lecture today. So we have completed just now for the correlation that we can use to determine the H value for forced convective heat transfer in pipes, right? For laminar or for turbulent or for the transition region. So the next part, the third part, we are going to look at the correlation that we are going to use to find out the H value for forced convective heat transfer outside various geometry. So this different geometry, it includes, okay, I think, okay, I didn't summarize here. So it includes the geometry that we are going to cover. It includes the plate, all right, and then the cylinder and sphere and banks of tube. These four general types that we will encounter most of the time in some process plant. Okay, now, so for heat transfer outside various geometry, right? So you can imagine it as something like this. Let's say if you have a tube, right? So the flow could be like this outside the cylinder, or if it's a flat plate, then which means it's something like this, or for sphere. All right. So then your H value, all right, and it will also then affect the heat flux. It will be dependent on the geometry, the position, go on here, happen. Okay, it will also depends on the position, right? Whether the flow is at parallel here, right, or whether it's from the flow only pass, let's say this side only, right? Or the proximity of other bodies, the flow rate, and the flow property. So which means this is related to the flow behavior, while the fluid properties are such as like the density, the specific capacity, the viscosity. Okay, so now, okay, let's look at here. Now, as mentioned, all right, the correlation, it takes this general form here, the general equation that allows us to calculate the average convective heat transfer coefficient, right, where you have the Nusselt number, all right, and most of the time here is your H multiplied to D, or it could be L, the length of the plate, divided by the thermal conductivity. Then the Reynolds number, rho VD, right, or the length of the plate divided by the viscosity, and the Prandtl number is the Cp, specific capacity, multiplied to viscosity divided by the thermal conductivity. And this C and M value, it then the Cm value, it will then be depends on the various configuration. Now, one very important thing when it comes to convective heat transfer outside the geometry, the fluid properties, right? So you may want to highlight this. The fluid properties, it will then be evaluated at the Flum temperature. So what is Flum temperature? So Flum temperature is the average, right? So it's the average of the wall temperature and the bulk fluid temperature. So which means you add up the wall temperature and the bulk fluid temperature divide by 2. Okay. Now, so it's given here the definition. Now, as for the velocity, right? So sometimes the velocity, all right, that is required for calculating the Reynolds number, we are using the free stream velocity for calculation. And if let's say the value is not provided, but you are provided the differential pressure instead, right? So then you can apply this formula here for calculating what is the velocity, right? So that you can apply it in the Reynolds number calculation. So it's the square root of 2 multiplied to the differential pressure divided by the density of the fluid. So you may need to apply this later in your forced convective heat transfer, right? Forced convective heat exchanger experiment, right? The lab report, you need to apply this one. Okay, now, so let's look at, oh, okay, it's here. So we are going to look at the correlation for these few types of geometry. So the first one, let's say if we have a flow parallel to plate, right, and of length L, so which means it looks something like this, right? So you have flow parallel to this plate here, and the length of the plate is L, right? Now, then it depends on the Reynolds number, right? So if the Reynolds number is between is less than 310 to the power of 5 and the Prandtl number is greater than 0.7, right? So for flow past a plate, this Reynolds number smaller than 310 to the power of 5 is considered as the laminar region, right? So always take note, I always tell students, take note that 2100 and 6000 only applies to flow inside pipe only. All right, that range that you all use to identify whether it's laminar or turbulent flow, 2100 and 6000, only applies to flow inside pipe. When it comes to other geometry, then the Reynolds number, the range of it for whether it's laminar or turbulent flow, it will be different. Okay, so for example, right, then this is your Reynolds number. It should be smaller than 310 to the power of 5. Then we will apply this one, right, where the Nusselt number is equals to 0.664 multiplied to Reynolds number to the power of 0.5 and Prandtl number to the power of 1/3. Okay, now if it's the turbulent flow region, which is given by here, if it's turbulent flow, it should be greater, the Reynolds number should be greater than 310 to the power of 5, right? And for this equation here to be valid, all right, you also need to make sure the Prandtl number is also higher than 0.7, right? Then we can use this Reynolds, this correlation here, which is 0. Nusselt number, equate it to 0.0366, all right, multiplied to Reynolds number to the power of 0.8, Prandtl number to the power of 1/3. Now, one thing that you need to take note is when you calculate the Nusselt number, right, because we're dealing with plates, then your Nusselt number should be convective heat transfer coefficient multiplied to the length of the plate, and this length here should be the length which is parallel to the direction of the flow. All right, and then divided by the thermal conductivity. So same goes to the Reynolds number. When you calculate the Reynolds number, right, the Reynolds number should be rho VL is no longer the diameter. Okay, rho VL divided by mu. And then take note also all this properties here, you have to find the properties which is at the Flum temperature, right? The wall temperature plus the bulk fluid temperature divided by 2. Right, same goes to the Prandtl number also. You have to evaluate it at the Flum temperature. Now, there's a special case if, let's say, right, if we are dealing with a rough plate, right? If it's a rough plate, now even if the Reynolds number is smaller than 310 to the power of 5, right? So it's also considered as turbulent flow. It's also considered as turbulent flow because, right, if you recall back, if the plate is rough, right, which means it will induce a lot of mixing, right, induce a lot of mixing in the fluid. So then it kind of behaves like a turbulent flow behavior already. So that's why even the Reynolds number is smaller than this value and the plate is rough, you will use this correlation for calculation. Okay, all right. So now let's look at the second example that we have today for the case of cooling of a copper fin. So let's say if we have a smooth, flat, thin fin of copper extending out from a tube, which is 55 by 55, 51 by 51 mm square. So let's see, this is 51 mm, this is 51 mm. All right, and its temperature is approximately uniform at 82.2 degrees Celsius. So let's see, T wall is at 82.2 degrees Celsius, and the cooling air, right? So let's say you have air that is flowing. So I'll write here the bulk fluid temperature is 15.6 degrees Celsius, and the pressure is at, okay, this is for air, pressure is at 1 atm. Okay, flows parallel to the fin at a velocity, right? So at a velocity, okay, V, which is equals to 12.2 meter per second. So now for laminar flow, calculate the heat transfer coefficient. So now then let's try and calculate to see if it's really laminar flow. All right. So okay. So if it's laminar flow, suppose we should be applying this correlation here, right? The one which is with 0.664. So I've copied it out here. Now then, okay. So we know that for calculation of Reynolds number is rho VL per mu. Okay, so before we can substitute what are the value for those properties, right, fluid properties, so we will need to find out what is the Flum temperature, right? So we need to calculate the Flum temperature, where is equals to wall temperature plus the bulk fluid temperature divided by 2. So now wall temperature, all right, is 82.2 degrees Celsius plus bulk fluid temperature is 15.6 degrees Celsius, divide by 2. So the answer should be around 48.9 degrees Celsius. Okay, so the fluid here, it refers to air, right? It's cooling air that we are dealing with, right? So then we will need to look at the physical property for air, which is at a flume temperature of 48.9 degrees Celsius. So it's again somewhere here, right? 48.9 degrees Celsius. So which means unfortunately you need to do interpolation, right, to find out what is the density, viscosity, thermal conductivity, and the Prandtl number. Okay, so now let's say if we have done the calculation, the interpolation, all right, the density at 48.9 degrees Celsius should be around 1.097 kilogram per meter cube, right? Viscosity, it should be 1.95, 10 to the power of negative 5 kilogram per meter second, right? And then the Prandtl number, if we complete the interpolation, it should be 0.704, and then thermal conductivity is 0.028 watt per meter Kelvin. All right. So okay, now so if we have all this data already, right, which is the data of the fluid properties, the air properties, right, at flume temperature. So let's start to substitute here to check whether it's in the laminar flow region here. So substituting the density, 1.097, okay, kilogram per meter cube, and velocity is 12.2 meter per second. The length of the plate, okay, 51 mm. All right, then divided by the viscosity is 1.95, 10 to the power of negative 5 kilogram per meter second. So if we complete this calculation, it should be equals to 3.49, 10 to the power of 4. Okay, 3.49, 10 to the power of 4. So let's check whether this value lies, yeah, so it's smaller than 3 10 to the power of 4, right? It's smaller than 3 10 to the power of, 3 10 to the power of 5, right? Smaller than 3 10 to the power of 5. So that's why, yes, we can confirm that it's in the laminar flow region, right? Laminar flow region. Okay, then only you can confirm that, yes, we can apply this correlation here. All right, so okay, then let us substitute all the data, all right, and calculate what is the h, right? So to find h, the length of the plate that is parallel to the direction of flow is 51, right, 10 to the power of negative 3 meter, and thermal conductivity is 0.028 watt per meter Kelvin. All right, so equals to 0.664 multiplied to Reynolds number 3.49, 10 to the power of 4, right, then to the power of 0.5, and multiplied to the Prandtl number 0.704, then to the power of 1 over 3. Right, so if you solve this, the H value, it should be around 60.7 watt per meter Kelvin. Okay, 60.7 watt per meter Kelvin. All right, so now if let's say instead of a smooth fin, right, but now the leading edge of the fin is rough, so that all the boundary layer of film next to the fin, it's completely turbulent, right? So this is the case where you have a rough plate, right? If you recall back, if it's for a case of rough plate, so directly you need to apply this correlation, which is for turbulent flow, right? So where Nusselt number is equal to the one which start with 0.0366, right? So I will not repeat it, all right? So but you can actually do it very quickly, because the Reynolds number, right, it will still be the same, right? It will be still the same Reynolds number value that we found just now. Here you substitute 3.49, 10 to the power of 4, all right? And then for Prandtl number, you substitute it with 0.704, right? Length of the plate is still 51, 10 to the power of negative 3, and thermal conductivity is still 0.028, because it's the same air. All right, so now then so all the properties are still the same, but you still get a different H value, because here the correlation is different, right? So if you compare both correlation, the C value, the M value is different, right? So if you solve this, the H, right, for this rough plate here, it should be equals to 77.2 watt per meter square Kelvin, which if you compare, right, just now, let's say for laminar flow, right, the H value is only 60.7. But when you have a rough plate, that it will create turbulent flow, right? So the H value is even higher, is 77.2. And so that's why when your H value increase, which means your rate of heat transfer, it will also increase, right? Because it's HA multiplied to the temperature difference. If this is constant, but this increase, then your rate of heat transfer will also increase. Okay, all right? So, all right, okay. Now, before I proceed to the next part, any question about this example so far? Any questions? Anyone? Or if it's all good, then you can give a thumbs up, then we can proceed to the next part. Okay, thanks Shawish for the confirmation. So, and admin too. So, okay, yeah? And I think there's no question in the chat area also. Okay, all right. So now, these are the correlation for the case when we are dealing with convective heat transfer, right, for flow past a plate, right? Remember, instead of diameter, you should be using the length, right? That is parallel to the direction of heat transfer. Okay, so now the next thing is, okay, if we have a cylinder with axis perpendicular to flow, now what does it mean? So now this case here is, for example, okay, I'll draw it here. Right, let's say if you have a cylinder, right, and the axis of the cylinder is here, right, the center, all right, and for flow that is perpendicular to the axis of the cylinder, which means your flow, it will be in this direction. Okay, it will be in this direction in the flow. Okay, so if that's the case, all right, so for flow, either for fluids, either gas or liquid that flows perpendicular to a cylinder, right, for example, it could be a copper rod, right, the general equation to determine the average heat transfer coefficient, and it holds with all heat transfer parameters evaluated at a firm temperature. So this one, you have to evaluate all the properties at firm temperature as well, right? So now, the general equation, it will take this form here. All right, Nusselt number equals to a coefficient multiplied by Reynolds number to the power of m and Prandtl number to the power of 1/3. So this Nusselt number, right? So we are dealing with cylinder, then which means it will be h multiplied to diameter divided by the thermal conductivity. Right? As for the Reynolds number, then it will be rho Vd per mu. Okay, so then what will be the C and the M value? Now, the C and M value, it will then be based on the Reynolds number. So which you can refer to the next table here, right? Depending on whether your Reynolds number is between 4 to 40, then the coefficient C value, it should be 0.911. All right, so just now the Nusselt number is equals to C to the power of this one, and then Prandtl number to the power of 1/3. So this would be your C value then, 0.911. While the M value would then be 0.385 if the Reynolds number is somewhere between 4 to 40 for flow that is perpendicular to the axis of the cylinder. Okay, so that's if it's a cylinder. And the next part is we are going to look at, let's say if we have flow past a single sphere. Now, for flow past a single sphere that is either heated or cooled by a fluid that is flowing past it, so which means something like this, a sphere. Okay, so the Nusselt number, right, same thing, is Hg over thermal conductivity. It will be equals to 2 plus, so the Reynolds number should be rho Vd per mu, all right, then multiplied to the Prandtl number. So this correlation, it will hold for the case where the Reynolds number is ranged from 1 to 70,000 and Prandtl number from 0.6 to 400. And think again, all your fluid properties should be evaluated at the flame temperature. Okay, so now let's look at the example, how we are going to solve it. All right, so I'll just brief you through this example because most of the data is the same as we have for the second example just now. Okay, so let's go through this example very quickly. Now, let's say referring to the same conditions of the previous second example, right? So still the air at 1 atm, absolute pressure, and it's at 15.6 degrees Celsius. It's flowing at 12.2 velocity of 12.2 meter per second. You need to find out what is the average heat transfer coefficient. For air flow past a sphere, which the sphere it has a diameter of 51 mm and an average surface temperature of 82. So meaning this case here, right, if we visualize it, okay, let's say if I draw it out, all right, so the diameter is 51 mm and you are informed that the surface temperature, right, TW is 82.2 degrees Celsius, while your air that is flowing, right, the temperature is at 15.6, pressure is 1 atm absolute, and the velocity is 12.2 meter per second, right? So now they want you to compare this to the value, right, later at when you have calculated the H value, right? Compare it to the convective heat transfer coefficient for the flat plate that is at turbulent flow, right? So just now, when we look at it, it's 77.2, right? Okay, so now let's say if you do the calculation. So before you can do this calculation here, right? So make sure you find out what is the film temperature, right? Film temperature, wall temperature plus the bulk fluid temperature divided by 2. So wall temperature is 82.2, right? Bulk fluid temperature is 15.6 divided by 2. So you should get 48.9 degrees Celsius. So all these data that you see here, the density, the viscosity is evaluated at 48.9, right? So now if we calculate the Reynolds number, I think this is the same answer as the, let me check. It's the same answer as the previous question. Yeah, previous example, 3.49 10 to the power of 4, because all the data is still the same, right? And then now, so with this, all right, so okay, its Reynolds number is 3.49 10 to the power of 4. Now, before you proceed, you need to check what is the correlation, right? So for single sphere, the lucky thing is we only have one correlation. So you just double confirm, right, whether your Reynolds number lies in this range here, right? So it's 1 to 70,000, so definitely fit, all right? And then next thing, let's check the Prandtl number. The Prandtl number should be greater than, it should be somewhere between 0.6 and 400. So your Prandtl number is 0.704. Okay, so which means also applicable, right? So this is the Reynolds number. So substituting it to the correlation, right, and equate it to the Nusselt number. So you can see here, right, H multiplied to the diameter of the sphere, 51 mm, right, divided by the thermal conductivity, right? So it should be equals to 2 plus 0.6 multiplied to Reynolds number to power of 0.5, then Prandtl number to the power of 1 over 3. Now, if they complete this calculation here, the H value is equals to 56.1 watts per meter square Kelvin. All right, but if you recall back, all right, so this is for the case of sphere. In previous example, when we deal with rough plate, right, which will create turbulent flow, okay, the H value is 77.2 watt per meter square Kelvin. Now I'll let you guess, right? Can you guess why there's a difference in this value here? Any suggestion? Any suggestion? Anyone? What possibly actually contribute to? Okay, let me see here. Okay, from Yihong's sphere has lower surface area available for heat transfer. Yes, correct. You are correct. So you can actually try to calculate it. What is the effective surface area that is available for heat transfer to occur? So for sphere, then it's pi d square, right? You can try to take some calculation. Well, area here, right, is 51 mm square just now. So if you do this calculation, okay, let me write plate, this is sphere. You'll notice later after the class, right, if you have time to explore it, you'll notice that the area of the surface area of the plate is actually greater than the surface area for the sphere. Okay, so you can try it out. Okay, so yep, okay, so that's the reason. Okay, so any questions so far for this example, the third example here? Any questions so far? Okay, all right. Few students say it's okay so far. All right, then let's take a 3 minutes break. I think you'll need it. Okay, let's take a 3 minutes break. Come back at 11:20. Then we'll continue with the banks of tubes and the last part, which is for convective heat transfer. Okay, come back at 11:21. Right now it's 11:18 already. Come back at 11:21. I have posted the passcode for attendance in the chat area, yeah? So you have 10 minutes from now to take your attendance. Okay, so you can refer to the passcode in the chat area, take the attendance. for 11:22. Alright, so let's continue with our lecture. Only two more parts, right? One is for flow past banks of tubes or cylinder, and then the last part will be about the calculating the H value if we have natural convection. Okay. Now we are still on the part for forced convective heat transfer outside a certain geometry, and now we'll be looking at if we have flow past banks of tubes or cylinder. Now this could happen. The more common example, it could be the shell and tubed heat exchanger, right? Where you have bundles of tubes that is being wrapped in a shell, right? So how you can look at it is as if you have this one, something like this. You have several pipes, right? Or you can say tubes also, okay? That it's arranged in this manner here. And then then your flow is actually perpendicular to the axis of the cylinder. Now, in this example here for shell and tube heat exchanger, it could be, for example, if you have, let's say, a hot water, right, that is flowing past this tube here, and then it's used to heat up, right, heat up some maybe air or gas that it flow past it. Or it could be the case where maybe it's cold water, right, cold water that used to cool down maybe air, hot air, or maybe steam. All right, so these are some examples of flow past banks of tubes. Now we have two different arrangement. It could be we can see here whether the tubes are arranged in an inline manner or is it in staggered manner. So you can see that all this on the left hand side here, the figure A, right? So all the tubes are arranged very systematically, right, in the same line, right? And however, right, if you look at part B, right, so the tubes are in staggered arrangement, right? They are not in line with each other. Now, then there are several news parameters that you need to understand. Okay, let me clear this drawing a bit, right? So the flow is actually in this direction, right? Take note, the flow is in this direction here, okay? And therefore, all right, so if we look at these two tubes, so the distance between the center of these two tubes here is denoted by Sn, where this one is the distance between the center of two tubes that is normal to the direction of flow. So this one we say normal to the direction of flow, right? So that's why you can see it use N to denote it, right? Whereas if we look at this one here, the distance between these two tubes here, right, the center of these two tubes is denoted by SP, which means is the distance between two tubes, the centers of two tubes, which is parallel, right? It's parallel, right? It's parallel to the direction of flow. Okay, Sn and Sp. And then other than that, this one you should know that then is it refers to the diameter, right? Then if you are looking for what is the distance between these two tubes here, then you should get Sn, right, divided by the diameter, right? Because the distance here is Sn, right? The whole distance is Sn, right? Then this part here is as if it's d over 2, right? Then you have 2 of this, which means it will then be equivalent to diameter. So that's why it's Sn minus d. Okay. Now for the staggered arrangement, then the Sn is still the same thing. It's the distance between the center of two tubes, which is normal to direction of flow, right? So then Sp is the distance between the center of two staggered tubes, or sometimes it can also be calculated as S prime P here, right? S prime P here. Okay, so now, okay. Now this is just now I've drawn actually also, right? So this is how it looks like. Let's say this is the flow direction, right? At certain velocity v infinity, and then the temperature of the fluid that is coming in is at T inlet temperature, but it will leave at some different temperature, either higher or lower, T out, right? And then this is the surface temperature. So this scenario here is very similar to what you will see later when you do the forced convective heat exchanger experiment, right? Something like this. But it's in vertical shape. Now it's arranged in horizontal, so you assume that it's vertical, right? So this is what happened, right? So in the forced convective heat exchanger, so sorry for my drawing, you have a centrifugal fan. centrifugal fan here at the bottom, right, that will draw in the air, right? So you draw in the air, and then the air here, it will pass through. So we have banks of copper tube, banks of copper tube. All right, and then this copper tubes here is connected to the heater, so it will heat up, right? So it will heat up this copper tubes here. So which means this copper tube here, it will be hold at some certain temperature, surface temperature Ts. So your air temperature, it comes in at a lower temperature, let's say room temperature 28 degrees Celsius. And when it flow past these banks of tubes, then it will be heated, and then it will leave at a higher temperature, let's say T out. Right, so this is what happens inside, let's say the case if we have flow past banks of tube with forced convective heat transfer. So it's forced convection because you have this centrifugal fan here that actually draws in the air, right? And then the fluid is flowing past the surface, and then it's outside, right? We are dealing with flow past outside the geometry. Okay, now, so if this is the case, right? So we are still using back the general equation where your Nusselt number is equals to C multiplied to the Reynolds number to the power of n, and then multiplied to the Prandtl number to some power of n. This I think it still keep at 1/3. Check. Yeah, it will still keep at 1/3, Prandtl number to 1/3. Then for what would be the C value and the M value that you are going to use, right? So it depends on the ratio, right? It depends on this one. The ratio of Sn to the diameter and Sp to the diameter. If both ratio is equals to 1.25, and depending on the arrangement as well, whether it's inline or it's staggered, then you shall select what would be your C value. So let's say if it's inline, right? So for the forced convective heat exchanger that we are going to do in our lab, your copper tube is arranged. Okay, great. I can't remember. You all can check, but I think it's inline. It's inline. All right. So then you have to calculate. So which means you have to measure, right? So if you have the copper tube, right, the flow is in this direction. So you have to measure what is the Sn value, right? And then you measure what is the diameter. Okay, so then you get the ratio of it, and then you measure here what would be the Sp divided by the diameter again. So if it's equals to 1.25 inline, right, then you should use this C and the M value. So you substitute here, right, C is equals to 0.386, and then the M value is equals to 0.592. Now, but however, you have to be careful here. You read through the this heading here. It says the value of C and M to be used for equation 4.61, which is this one, right? This general equation here for heat transfer to banks of tube containing more than 10 transverse row. So this C and M value is only applicable to more than 10 transverse row. So what does it mean by more than 10 transverse row? So the 10 transverse row, it refers to like this, right? How many more rows that is perpendicular to the direction of flow? So it's okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in this manner here, right? There should be 10 rows. All right, then you can apply this C and M value directly. But for your forced convective heat exchanger experiment, I think if I'm not mistaken, there's only 4 rows, right? There will be only 4 rows. Now, then how are we going to solve it? So if there are only 4 rows, we will need to apply some correction factor, right? So think of this one, the value only valid for 10 transverse row. So if you have less than 10 transverse row, then we'll need to refer to table 4.63, right? So it depends on how many number of transverse row deep, right? Then you need to apply this correction factor for the H value, right? So let's say for our experiment, there are only 4 transverse row deep, right? And then it's inline, right? It's in inline manner. So then when we calculate the H value, we'll need to multiply it to 0.9. So what it means here, all right, so let me show you. So we know Nusselt number is equals to, so let's say just now, all right, so let's say the ratio is 1.25, just example, it's not the answer for your lab report, okay, all right, just example now that I'm giving, all right, so let's say C is 0.386, right? I'll note it down here, 0.386. Then Reynolds number to the power of 0.592, right? Multiplied to Prandtl number to the power of 1/3. And then you equate it, right? So the Nusselt number here is D over thermal conductivity. All right, so then you proceed to substitute what is the diameter, what is the thermal conductivity. Then okay, you have solved the H value, right? So let's say I just put some dummy value, so 50 watt per meter squared Kelvin. All right, then you apply it for your heat transfer calculation, right? So where is your convective heat transfer coefficient multiplied to area multiplied to temperature difference. Now, but you have only, so this value here that you apply, the C and N value, it only applies for 10 transverse row D for inline arrangement. But we have only 4. Then some modification has to be done on this H value here. So 4 rows, right, inline arrangement, then the correction factor, it will be 0.9. So how we do it is we'll then multiply your H with 0.9, right? Then multiply to area, then multiply to the temperature difference. Right? Then you can proceed to find out what is the rate of heat transfer. Okay, all right, so that's how you can do it. So no worries, for this one, I'm not discussing any example on this, but I have uploaded the complete reference material, a complete example under the lab, the practical section, practical session part on my times. So make sure you go through it when you're preparing the lab report. So it's a very complete and detailed example that guide you on how to solve the calculation part. All right, so you'll need to do some trial and error. It takes some time, trial and error, right? So because if you recall back, right, so what happens in this case here is where, okay, for example, this is the banks of copper tube, right? There are 4. Okay, your air flows in this direction, that is normal or perpendicular to the tubes, right? So the air enters at inlet temperature Ti, it leaves at outlet temperature To, and then your copper tubes is being heated to surface temperature of Ts. So don't forget, when you evaluate any properties, right, when you're calculating your Reynolds number, the Prandtl number, all this you need to evaluate at the flame temperature, which is actually the wall temperature plus the bulk fluid temperature divided by 2. Now, but the problem here is your bulk fluid temperature at the inlet and the outlet is different. So which means this value here, it depends, right? So if for those who have done the experiment, then you may have an idea, because we do not measure this one here. We are not measuring the outlet temperature. We couldn't measure it. What we measure is only the inlet temperature of air and the surface temperature. So which means this is a value that you will be guessing, right? So then this value here, then it will be also a guess value, right? So you need to then do a trial and error. So you can now imagine, right? Right, depending on the guess value, it will all affect your properties and then eventually all the calculation here, right? So that's why I mentioned you need to do trial and error. So you can use Excel to help you with that. That's what some of the previous students, how they did it, so that it could help them with the calculation of the trial and error thing. So I think by the 3rd iteration, you should be able to find the most accurate outlet temperature already of the air. All right. So the best thing is go refer to the example. All right. Refer to the example I posted. Then you have a better idea of how to calculate this. Okay. So but for the general part, right, the introduction part to this one for flow past banks of tubes, right, the concept. Any questions so far? Any questions so far, everyone? Okay. All right. Just give me a minute to check on the attendance part. Only 15 students taken attendance so far. How about others? I think there should be 2 more, right? So I will share the passcode here again in the chat area. It's a new passcode for another 10 minutes. Okay, please refer to the passcode in the chat area. While I continue with the last part of our lecture today, which is for the case if we have natural convection, right? So now For natural convection, okay, so now in process engineering, this type of phenomena, it may occur, for example, here you have a radiator, right, to heat up a room, right, or here in general, right, a hot vertical plate that is used to transfer heat to gas or liquid adjacent to it by natural convection. So as we know, natural convection, it occurs due to density difference, right? So because of the heat, the temperature difference, it will induce density difference, then it will bring about the buoyancy force that causes the mixing, and therefore there will be movement of fluid, but it will be a very, very, very slow rate, which you can refer here, right? So this is here an example of what happens to the velocity profile. So as compared to fluid flow, right? So our velocity profile, it looks something like this, right? But if you compare here, if it's natural convection, you notice that the velocity profile is somewhere like this only, okay? Where most of the the higher flow rate, it occurs at somewhere still not very far from the plate. Well, when it's at a distance away from the plate, the velocity almost comes to zero here. Because why? Because the heat it is not penetrate very deeply enough into the bulk fluid yet. So that's why you observe here, right? So the mixing, it didn't quite reach this part when it's further away from the plate, right? That's how the velocity boundary looks like for, let's say we have natural convection. Okay, now, so let's see for a case of natural convection from vertical plates and cylinder with height length, right, which is smaller than 1 meter, all right, the average convective heat transfer coefficient, it can be calculated using this correlation here for vertical planes and cylinder. Okay, so if you look at the left hand side, all right, this is actually, again, your Nusselt number, right? So it depends whether you are dealing with plates, then you use L, or diameter if you are dealing, or even if it's cylinder, all right, so we can also use the length, all right? So then as for this part here, okay, this section here, that if you look at it, this whole chunk is what we call the Grashof number, right? It's the Grashof number, which it represents the ratio of buoyancy force to the viscous force, right? For it to float, and this one is because of the momentum, right? In free convection, and it plays the role similar as the Reynolds number in forced convection, right? Well, the second part here, it gives us the Prandtl number. Okay, now, so what is this beta here? If you look at the Grashof number, right? So we have the length to the power of 3, the density to square of the density, then G is the gravitational acceleration, 9.81, multiplied to the temperature difference divided by the viscosity, the square of the viscosity, and you have a term beta here. So this beta here is known as the volumetric coefficient of expansion. Right, so it's so how we calculate it, the beta value is equals to 1 over the film temperature. So which means before you can find out what is the beta value, you need to calculate what is the film temperature. Okay, the film temperature. All right, so now then if you look at here, right, so you have unknown coefficient A and the power of M here. So how do we know what are the values that we should use for the A and M? Now, there you refer to figure this one, table 4.7. For some of the constant that you can use for this equation here, depending whether you are dealing with vertical planes and cylinder, right, or is it horizontal cylinder, all right, and horizontal plates, all right. So depending on the product of your Grashof number and Prandtl number, so you check for the range, then you can refer to what is the A value and the M value that you should apply to this correlation here. Okay, right? So now let's try the last example so that you have an idea how we can apply the correlation. Okay, so here a heated vertical wall, which is 0.305 meter high of an oven for baking food with a surface temperature of 505.4 Kelvin. So this is the wall temperature. It's in contact with air, and the air is at 311 Kelvin. So which means this is the TB, right? Okay, bulk fluid temperature, T 311 Kelvin. So calculate the heat transfer coefficient and the heat transfer per feet, or which means per length, per width of the wall. Right. Note that the heat transfer for radiation will not be considered. And then, so you can see some data given here is in English unit, but we are focusing only on the SI unit. Right now. So the first thing, we'll need to find out what is the film temperature so that we can later use it to determine what are the properties of the fluid. So the fluid here, it refers to the air. Okay. So you can notice now, right, towards the end of the lecture already, right? So it's only for flow in pipes we'll use the bulk fluid temperature to evaluate the properties of the fluid, right? Then other than that, when you have flow outside the geometry, when you have natural convection, all your properties should be evaluated at the film temperature. Okay. Now, so let's solve the film temperature first. So the film temperature, all right. So wall temperature given just now is 505.4, right? Okay, and then Kelvin plus the bulk fluid temperature is at 311 Kelvin. So which means it's actually, let me see, the air is at a lower temperature. So this would be the case. So yeah, the wall here is used to heat up the air. All right, so divide by 2. So the film temperature is equals to 408.2 Kelvin. All right, so once I've calculated the film temperature, okay, so then you can proceed to find out what is the physical property of the air, right? Physical property of air. Okay, let me see here. So the physical property of air, so you refer to all those data which is in SI unit. Let me see if I can show you here. Oh, all is in let me see here. It's in English unit here, I think. Oh, okay, yes, there is those in SI unit. Okay, I can see now. The density, okay, if we evaluate it at 408.2 Kelvin, the density of air is 0.867 kilogram per meter cube. Prandtl number, no matter what is your English or the SI unit, is the same because it's a dimensionless number, right? And then for the viscosity, let me see. So viscosity is 0.232, right? Centipoise, right? So you may need to do a conversion. Let's see. And the beta value, all right? So here, before you proceed further, right? So you can also, after calculating the film temperature, you can also proceed to calculate the volumetric coefficient of expansion, right? 1 divided by film temperature. So it should be equals to, let me check what is the value. Film temperature. Okay, so it should be equals to 2.45 10 to power -3 per Kelvin. All right, so I think it's written here as well. Yep, the beta value is this equivalent to this one. Okay, then after that we'll need to calculate the temperature, right? The temperature difference as well, but you can substitute it directly into the calculation, right? So we'll do it directly in the calculation. So if we have everything already, okay, let me check something here. Okay, yeah. Okay, so now we can start to substitute. So Grashof number is equals to the length of the vertical wall, so it's mentioned is 0.305 meter. So multiplied to the density, so we have to square it. So density is 0.867 kilogram per meter cube. All right, so we square it, multiplied to 9.81 meter per second squared, right? Then multiplied to the beta value. The beta value that we found is 2.45 10 to the power of -3 per Kelvin. All right, and then multiplied to the temperature difference. So it has to be in Kelvin because here your film temperature, right, your beta, your volumetric coefficient of expansion, the TF, the beta value is in Kelvin, right? So when you calculate the temperature difference, it has to be in Kelvin as well. So it would be 505.4 minus 311. Okay, then divide by the viscosity. Okay, let me see what's the viscosity value. Oh, yeah, let me check. So, okay, the viscosity is 2.3232 10 to the power of -5. So we have to square it as well. So if you solve this, the Grashof number, it should be equals to 1.84 10 to the power of 8. All right. So now, if you recall that the correlation that we should be used to solve natural convection here is Nusselt number equals to the Grashof number, right? And then multiplied to the, I think it's Prandtl number, yeah, Prandtl number to the power of n. Is it m that we are using? Yes. All right. So we've found the Grashof number already. So you need to find out what is the product of this, right? So if you refer here, we need to find out what is the product of this, then only we can decide what is the a and n value. So then on the next step, all right, so you need to calculate the product of Grashof number and Prandtl number, right? So 1.84 10 to the power of 8 multiplied to the Prandtl number 0.69, it would then be equals to 1.27 10 to the power of 8, right? So that would be the product of Grashof and the Prandtl number. And take note that we are dealing with vertical wall, right? Okay, now we can then refer to here. Okay, so for vertical wall, and our product of Grashof and Prandtl number is 1.27 10 to the power of 8. So which means it lies between, right, this range here, right, 10 to the power of 4 and 10 to the power of 10 to the power of 9. So which means your A value should be 0.59, right? And then the M should be 1/4. Okay, so now I'll directly skip here for you to see. Okay, here. All right, so then we can substitute. This is the A value, all right, and then this is the M value, 1/4. All right, then substituting the K value. Let me see. Okay. Let me show you the step in SI unit. Okay, K that we found is 0.0343, right? At the film temperature, and the length of the plate is 0.305, right? Let me check. Yeah, 0.305 meter. Okay, substituting it. So this is the K value. You rearrange it, right? And this is the L value. Okay, then 0.59, which is the A value just now. And then we have so just now, right? The product between the Grashof and the Prandtl number is 1.27 10 to the power of 8. And then the M value from the table just now is 1/4. So substituting this, then we'll get 7.03 watt per meter square Kelvin for natural convection, right? So now if you recall back, right, so as compared to what we have been calculating just now, for example 2 and 3, where the where the convective heat transfer coefficient, the H value, is for sphere is around 60 plus, right? Then for plate, it's around 70 plus as well, right? If it's turbulent flow, it's much greater than this value that we are calculating. So most of the time for natural convection, right, the H value would be somewhat similar than smaller than 10 or so around 10, 11, 12. It will be a very small value. All right. So they also ask us to solve for the heat transfer per unit width, right? So or let's say if we calculate just the rate of heat transfer. So completing it, all right. So it will be okay. So 7.03 watt per meter square Kelvin. All right. So it's a plate. And we know that the length is 0.305 meter on each side, right? So we just square it. So this then will give us the surface area of the plate. And then for the temperature difference, so let me check what is the temperature difference. I've forgotten. 505, right? So it's 505.4 minus 311 Kelvin. So if we solve this, the rate of heat transfer is equals to 127.1 watts. Okay, all right. So this is for the example of natural convection. Basically, is to introduce you to this equation here, right? This correlation here and this table, right? Depending what's the geometry that you're dealing with, referring to the product of Grashof and the Prandtl number, then you can find out what is the A and the M value. All right. So Any questions so far for this example? Any questions so far? Is it okay? Anyone? Can someone help to confirm? Okay, thank you, Shawish. All right, so if there's no further question, okay, that's the last part of our subtopic today that we are discussing. So for today, our lecture, we have looked at the different dimensionless number, right? The Reynolds number, the Nusselt number, and the Prandtl number. And we have also looked at the correlation for calculating the H value for flow in pi, right? For, let's say, the laminar, turbulent, and transition region. So take note, very important thing, the property should be evaluated, right? Should be evaluated at the bulk fluid temperature, okay? Except for the viscosity at the wall temperature, right? Whereas the rest that we are discussing today, force convective heat transfer over, let's say, a flat plate, or is it a cylinder or sphere or banks of tubes, and for natural convection, right? So for all this, right, the properties should be evaluated at the Flum temperature, right? Okay, take note, Flum temperature, which is the bulk fluid temperature plus wall temperature divided by 2. Okay, so these two important points here you have to remember. So, and for all correlation and equation, you do not need to memorize it. It will be provided during your final exam. Okay. So now let me see if everyone has taken the attendance. Okay, only 16 so far. Now, so if you have no further question, then I think that's all for our online lecture class today. I will share with you the recorded the pre-recorded lecture video in case if you want to refer back maybe during revision later before final exam. And then tomorrow, all right, tomorrow 4 to 6 we have our tutorial. So yeah, then please remind me to discuss with you the replacement class for week 9. I just noticed that week 9 Monday is also a public holiday, so we'll need to plan for the replacement class. So I'll discuss with you tomorrow when most of your yeah, we can meet face to face. It's easier to confirm. All right. So as for week 7, as we discussed earlier, week 7, right, there's no replacement class for lecture. So you can watch the pre-recorded lecture video that I've already uploaded last week, right? It's about the Navier-Stokes equation, so that you have more time to like replay back or rewind back any section that I'm explaining in the video. Okay. So yeah, I think that's all for today. All right. So if I've taken your attendance and no further question, then yep, you can leave already. And I'll see you tomorrow. Okay. Thank you. Thank you very much, everyone.
Thank you, Miss.
Thank you.